Refractive index distribution in the human crystalline lens. One of the most important part of our eye is the crystalline lens, which is here after our pupil. That part of our eye, we cannot consider it as a part or optical element with constant refractive index. So there is a lot of model to actually predict the refractive index of this part of our eye. But one of the most important model is the gradient refractive index, which means that the refractive index continues, but it changes in different direction in z and y direction. This part of our eye, that we call it lens or crystalline lens, has two important surfaces. The first surface, we call it anterior surface, and the second surface, which is the back surface, we call it posterior surface. So in order to model any optical model for this part of our eye, we have two different models. One of them is multiple layered shell structure, which we consider the whole structure as a different layers with different refractive indexes, and we have a lot of scientists that follow in this model. And there is another model, which is most of the time when we're gonna model it in Zmax, we use this model because it's much easier. There is a function in Zmax to put a gradient refractive index. So this model, which one of the most important paper in this model is from Gostran, 1909. In this model, there is a general mathematical form for representing the refractive index distribution in y and z direction. Because the system is rotationally symmetric around z, usually we don't consider x direction as an important axis, because the whole system is rotationally symmetric around z axis. So this is our z axis, this is the y axis, and since the system is rotationally symmetric, and in Zmax we usually take a look at yz direction. So the refractive index of this part of our eye, crystalline lens, is a function of both y and z. So the whole function is equal to n naught z plus ny, this is a function of z, multiplied by y to the power of 2 plus n2 is a function of z, multiplied by y to the power of 2, and we continue this equation with all even powers of y. The reason that we don't have any odd number is that this system is rotationally symmetric. If you put any, for example, y to the power of 3 into this equation, then for negative y you get, for example, at this point you get another number, for positive y you get another number, and it's not going to be rotationally symmetric. So we only have those power of 2, 4, 6, blah blah. So even each part, for example, n naught z is a function of z, so we can Taylor expand this part of the equation. N naught naught, this is n0 0, this is a constant number. N0 1 times z, N0 2 z2, N0 3 z2, we can continue to large powers of z. And n1z is the same, but the index is different. You know, here we have n10, n11, and n2z is the same. So you can see in this photo, this is a Gostran model. We have contours of constant refractive index. The shapes are like this, depends on, you know, what are those coefficients, n00, n01, n02, and the rest of the coefficients. So right now let's take a look at one of the models, Liu and Brennan in 1997. We have refractive index coefficient. Grade A means gradient lens function or gradient in refractive index of anterior surface, and grade P means gradient for posterior surface. N00, as I said, we can consider it as a constant or average of the refractive index, which we have 1.368, which is pretty close to the refractive index of the water. And it makes sense because, you know, most of the materials that we have in our eye is from water, so the refractive index is pretty close to water. And for N01, which is, you know, we have N00 here, N01 multiplied by Z, and then from this equation goes to here, which we don't have any power of Y, is 0.04, very small number, and the rest, it can be negative, it can be positive. So in this equation, for n0z, we have n00, n01, n02. For the rest, because we don't have any value, we just put 0 for the rest. So that's the n0z. We have this function based on those numbers. And the next index is n10. We only have a constant number for here, and this constant number is going to get multiplied by y to the power of 2. So we only have 4 constant for actually define the whole lens in our eye. So by those numbers is available online in different papers. We can get a little bit different values, but we have those values and we can import them into Zemax and model that part of our eye. And here some of the references that I use for this presentation. Thank you very much.